Good afternoon, Southminster scholars. Today we're going to study Pluto and the definition of a planet. Our solar system is best understood as 6 families of objects, each with similar characteristics of size, orbit, composition, moons, and rings. As we learned last week, Pluto is a member of the Kuiper belt. There are 8 planets. Over the years, the number of planets have changed. You might ask, why is that? It's because of our ever-increasing and greater technology. It's enabled us to redefine what exactly is a planet. The discovery of Eris, E-R-I-S, a Kuiper belt object larger than Pluto, brought this point to the forefront. Today, Dr. Summers will guide us through these discoveries.
How many of you have heard this phrase? My very energetic mother just served us 9 pizzas. I'm sure that many of you memorized it in school. It is, for those who know it, a mnemonic for the 9 planets. This is the mnemonic for Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. But in the modern solar system, that's no longer accurate. That's the viewpoint we had at the beginning of the space age. As my kids tell me, Dad, that's so last millennium. We now only count 8 planets, and the structure of the solar system can't be viewed so simplistically as just being the sun and the planets. In this course, we have progressed through various perspectives on the solar system. The geocentric, the Earth-centered geometry of the solar system, the heliocentric, the sun-centered philosophical shift, the gravitational perspective, where the orbits of the planets were physics-based, and the space-age perspective, where we move from being observers to being explorers of our solar system. We have now filled out our knowledge to take on the 21st century view of the solar system. This view is based on the idea of families of objects. We have the sun in the center. It is surrounded by the rocky planets. Outside of those are the asteroid belt. Then come the giant planets, followed by the Kuiper belt, and out at the very edge, the Oort cloud. These 6 families define the basic structure of the solar system. And this bullseye diagram is a useful way to mentally organize the structure of our solar system. Now, I've presented these ideas for about a decade. And I've had kindergartners tell me, but wait, Pluto is still a planet. I read it on the internet. Well, I try and be gentle with them, and I ask them to give me some scientific arguments and not just rely on authority, whether it's my authority or the questionable authority of the internet. At the Space Telescope Science Institute, we developed a lesson plan where the kids sort the solar system based solely on the data. And what we found is that the adults, the teachers that we give it to, they like it even more than the kids. Here's what we do. We start with a table of numbers. These are the characteristics of 16 solar system objects. The number of moons they have, their orbit size, the orbit shape, the orbit inclination, their size, their mass, and their composition. Now, what's most important about this table is that we don't identify the objects with names. We just give them numbers. We want the sorting to be anonymous. When you look at a table of numbers like this, those of you who have math phobia will be scared by it. Many people are, oh wow, this table of numbers just scares me. I gotta say, as an astronomer, I just love tables of numbers, and I start looking at them and trying to sort them in my head. But to make it more friendly for most people, what do? You graph them. So here is a graph of the number of moons. And you can see very easily, right, just looking at the graph, that most of the objects have very few moons or no moons. And there are 4 objects that have many moons. If we look at orbit shape, you can see again a trend that the dominant number of objects have roughly circular orbits. And there are some that are more elliptical. And then there's one way up here around an ellipticity of 0.45. Number 4 has a strongly elliptical orbit. Then you could look at orbit tilt. And again, you get the same sort of characteristic that there are most of them less than 10 degrees away from the ecliptic plane, and then some that are more tilted, and the maximum here is also object 4. That suggests that the characteristics of orbit shape and orbit tilt might be correlated. So what you can do then is plot orbit shape versus orbit tilt. And indeed, you do find a rough trend. The objects that have a more elliptical shape in their orbit tend to have more tilted orbit. Conversely, those with more circular orbits, those who are lower on the plot, will tend to be more left. This sort of linear correlation, it's a rough linear correlation between orbit shape and orbit tilt. This is how you explore the data of the solar system. And you can make lots of plots and explore many different trends, but the punchline comes when you plot the size of the object versus its distance from the sun. And immediately you can see 4 distinct groups fall out. The objects are grouped not only by their different distances away from the sun, there are different regions as you go out from the sun, but they also are grouped into different sized objects. And the different regions all hold different sized objects. Furthermore, if you look at the compositions of these objects, you can see that each group has a distinct composition. This group over here is rocky. This group are all gaseous. These are ice and some rock. These are rock and some ice. Furthermore, you can see other correlations by going back to the data table that these objects up here, the gaseous ones, they all have many moons. And these rocky ones and these gaseous ones, they have mostly circular orbits. And the other 2 groups down here and in the bottom, they have more elliptical orbits and more tilted orbits. Just by examining the data, you can start to pull out the groupings in the solar system. Now, these groupings are, of course, the rocky planets over here, the gas giant planets up here, or the giant planets, as they're sometimes called, up here. Down bottom, we have the asteroid belt. And over here on the right in the bottom, we have the Kuiper belt. The data selection that goes into this plot is biased only in that I chose the 4 largest members in each of these 4 groups. But a full plot of all the objects in the solar system still would, well, I guess it would be a lot messier. There would be stuff, scattering in and out from the Kuiper belt and the asteroid belt, but the 4 groups would still be blatantly obvious. So this 21st century solar system, this diagram that I'm promoting here, is not some organization that is imposed upon the solar system from without, but rather it grows naturally out of the data. So if you want to memorize the new solar system, you need all this: Sun, Mercury, Venus, Earth, Mars, asteroid belt, Jupiter, Saturn, Uranus, Neptune, Kuiper belt, and Oort cloud. Well, I took this as a challenge, and I came up with this. Science may view established models as basic justified standards until new knowledge bears out changes. Now that was intentionally tongue-in-cheek, using the mnemonic to comment on the situation. And I know if people were actually going to try to memorize this, they wouldn't want to give up on their very energetic mother that easily. So we came up with an alternate one. Sometimes my very energetic mother also boils jumbo shrimp using 9 kettles bubbling over coals. That is the new solar system, and it's quite a mouthful. At this point, somebody always asks, what about Pluto? Well, Pluto fits neatly into the Kuiper belt. It was number 8 in those plots, and its characteristics, as shown in those plots, are the same as the other Kuiper belt objects. By the way, number 4, the outlier in those two plots, that was Eris. Pluto is no longer an oddball. It now has a family. But people still say that I learned Pluto was a planet. What happened here? And to that I have to respond, what is a planet? Because if you look at the history, the number of planets and the definition of a planet has fluctuated strongly. Let's start with the geocentric model. The Earth is at the center, and then you have the Sun, Moon, and 5 planets. Of course, the Sun and the Moon, they move across the sky. They're like planets, so perhaps you could call it 7 planets. And then we move to the heliocentric model. In 1543, we had the Copernican revolution, where Earth became a planet. And we determined that the Sun was at the center and the Moon orbited around Earth, so they're definitely not planets. So now we have 6 planets. In 1610, Galileo discovered the moons of Jupiter. Here are some of his notes observing the moons of Jupiter moving around Jupiter. And these moons of Jupiter were called planets at the time. So then we jump to having 10 planets. Later, Huygens and Cassini discovered 5 moons of Saturn, so you could say we had 15 planets. Although I'll note in 1698, Huygens refers to them as 10 secondary planets. Earth has 1 moon, Jupiter has 4 moons, Saturn has 5 moons, that makes 10 moons. So these are now called by him secondary planets, so really we're back to 6 major planets. In 1781, William Herschel used this telescope here, this measly little 7-foot telescope. He used this to discover Uranus. Then we had 7 planets. And more importantly, Herschel showed that new planets could exist. It was also fashionable at that time to use the Titus-Bode rule, which predicted the positions of a planet in the solar system, in their distances away from the sun. Important point is that the Titus-Bode rule predicted a planet between the orbits of Mars and Jupiter. In 1801, Piazzi discovered such a planet. It was named Ceres. And so the missing planet was found, and now we had 8 planets. But that didn't last long. In 1802, Olbers discovered another object in the same area, Pallas, 9 planets. 1804, Harding discovered Juno, 10 planets. And in 1807, Olbers again discovered Vesta, 11 planets. These are what we now consider the 4 largest asteroids. And here are their orbits. You can see that all 4 of them orbit between Mars and Jupiter. Things are looking a little messy, but they sort of fit with the Titus-Bode rule. Except in 1845, we added a 5th asteroid, Astraea. Now we have 12 planets. In 1846, there was a new planet predicted by these 2 gentlemen. On the left side is Urbain Le Verrier, he was French, and on the right side is John Couch Adams, he was English. They both predicted a new planet outside of Uranus based upon the perturbations observed in the orbit of Uranus. They couldn't get anybody to look for it in their own countries, so it actually ended up that the Germans discovered it. That was Neptune. Neptune, when it was discovered, was the 13th planet. Shortly thereafter, in the 1850s, we reclassified the asteroid belt. All of those 5 objects that had previously been discovered became part of the asteroid belt, and that's a good thing, because hundreds of these asteroids were discovered in this region between Mars and Jupiter in the ensuing decades. So after being up in the teens, the number of planets is now down to 8 again. During the 1850s, we also had a couple of mistaken discoveries of planets. In 1851, there was a discovery of a planet at 137 AU. That's 4.5 times Neptune's distance from the Sun. 9 planets. In 1859, Lescarbault sees a planet transit the Sun, and he calls it Vulcan. This perhaps would have been ignored, except for 6 months later, Le Verrier, who had predicted Neptune, also predicted a planet interior to Mercury. So now we have 10 planets. It wasn't until 1879 that the error was found in that way outer planet, and so then we go back to 9 planets. Vulcan for its part, was never observed again, and in 1916, general relativity was able to explain the orbit of Mercury, so it showed that there never was any need for a Vulcan. Again, back to 8 planets. At the same time, Percival Lowell was searching for planet X, and in 1930, this man, Clyde Tombaugh, found Pluto, and Pluto became the 9th planet. It stayed that way until 2006, when the International Astronomical Union demoted Pluto to become a dwarf planet. And once again, we're back at 8 planets. Note that the 2006 IAU definition was actually the first official definition of a planet. There were a lot of unofficial definitions previous in history. You see, the word planet comes from a Greek word that means wanderer. These are the wanderers in the night sky. While the sun and moon and stars showed regular motions, the planets wandered back and forth. They showed retrograde motion. In the heliocentric view, the planets were the objects that orbit the sun, and then moons would orbit around planets. Later, as we got into the gravitational perspective of the solar system, Kepler's laws defined how planets should behave. An object was a planet if it followed Kepler's laws. Although, for some reason, comets didn't count. We knew of a lot of comets then. They obeyed Kepler's laws, but they didn't count as planets. A bit later, when the Titus Bode rule was in fashion, planets were those objects that were specified by that rule. When Uranus was discovered, it was consistent with the rule, and the first asteroids, they were consistent, but Neptune didn't fit. So then we fell back to what I would call a non-specific definition of a planet. And really, that was the definition I grew up with. Planets are the major objects orbiting the sun. We just don't specify how we define major. Now we come to Pluto. Pluto was originally estimated at 7 Earth masses. 7 Earth masses. That qualifies it as a major planet. However, soon it became the incredible shrinking planet. It was quickly seen to be smaller than predicted. As early as the 1940s, the estimates of its size had gone down to about 1 Earth mass. And as observations got better and better, the estimates of Pluto's size got smaller and smaller. In 1978, its moon Charon was discovered. And this helped reinforce the idea that Pluto was a planet because planets have moons around them. Pluto has a moon, reinforces the idea that it's a planet. Still, the 1980 estimate of its mass was 1/10 of Earth's mass. I actually have seen a very humorous plot made by a scientist that plots Pluto's size versus time, showing it how it decreases. And if you extrapolated that plot, it should entirely disappear before the year 2000. Well, in 1985, we had Charon transit in front of Pluto, and we were able to get a real size and mass estimate, and it was tiny. Pluto's mass is only 2/1000th of an Earth mass. Our moon is 6 times more massive than Pluto. Here is a comparison of the 7 large moons of the solar system with Pluto. All of them are larger than Pluto, and you can see Pluto's kind of fuzzy here, but unfortunately, that's the best image we have of Pluto. So it sort of makes you question, why do we call it a planet? Furthermore, starting in 1992, we discovered all these objects in the Kuiper Belt. These are all in the same region of space as Pluto, and they all have similar characteristics. So when we were building the Hayden Planetarium in 2000, this is the Rose Center for Earth and Space, and the Hayden Planetarium is located in the top of that sphere. When we were doing the exhibits there, we decided not to call Pluto a planet. The reason, and my fellow curators and I discussed this at length, was that first we wanted to adopt a 21st century view of the solar system, and more importantly, we expected that Kuiper Belt objects larger than Pluto would be found. And we were creating exhibits that had to last decades. Well, it happened faster than we actually thought it would happen. In 2003, Eris was discovered, and it's 10% larger than Pluto. And this is the discovery that forces the issue. Because you can't continue to call Pluto a planet without also calling Eris a planet. As it turns out, the International Astronomical Union had already been trying to define planet. For several years, they'd had a committee of experts meeting, but the experts could not reach consensus. Some of them demanded that Pluto remain a planet, and some of them demanded that Pluto not be considered a planet, and they just couldn't come to an agreement. So in 2006, they formed an alternative committee, and they created a proposal. Now, to understand the proposal, first you must understand the definition of a star, which is something I think everybody agrees on. Stars are powered by nuclear fusion in their core. And normal stars use hydrogen fusion. They fuse 4 atoms of hydrogen and make 1 nucleus of helium. For lower masses, you can also have fusion that occurs for deuterium, also known as heavy hydrogen. And deuterium fusion can occur for objects that are about 15 times the mass of Jupiter to about 70 times the mass of Jupiter. We call these objects brown dwarfs. So, the initial proposal at the IAU of how to define a planet was this. First, it has to orbit a star. Second, it has to be small enough that it avoids any type of fusion, deuterium fusion or hydrogen fusion. Third, it has to be large enough for gravity to make it spherical. In that proposal, they defined 12 planets, taking the usual 9, adding in Charon as a planet, adding in Eris as a planet, and also reinstating Ceres as a planet. Now, when this proposal was examined, some folks said it implied that there were actually 40 planets in the solar system, not the 12 in the proposal. The big problem with this whole proposal was that the committee fully expected rubber stamping of it. Basically, they had a full press package ready to go and released it when they released the proposal. This was before any astronomers had even seen the proposal. They released the ideas to the media. This is a phenomenally stupid way to try to do science. Of course the proposal would be revised. And 1 week later, proposal number 2 was put to a vote in the IAU. This one added the requirement that to be considered a planet, you must dominate your orbit. It also added the idea of a dwarf planet. So Pluto, Eris, and Ceres became dwarf planets, and Pluto lost its planetary status. We moved down to 8 planets. This resolution was passed in a vote of perhaps 500 folks. The whole thing was really needlessly rushed. It didn't satisfy anyone, except, of course, the media. Because the reaction to adding planets to the solar system was huge. It was all over front page news of the papers. And then a week later, the reaction to then demoting Pluto was even bigger. The astronomers who were not at the IAU meeting voiced dissent, and no one I know wholeheartedly supported either proposal. Some openly ridiculed the resolution, and the press ate it up. I think this is a bad time from our community because we look like a bunch of squabbling third graders. The major mistake made at the time, and for a long time afterwards, was it's really not about Pluto. It's not about the status of one object. It's about the whole solar system. And science really can't be done in a 1 week meeting. If you're going to try and do a nice definition, present it to the community, give them 6 months to comment before you take the vote. But this is the way things stand. We can, however, make an attempt to do a scientific view of a planet definition and see if one can be found. Now, everyone seems to agree that no fusion is a good start. Being small enough to avoid any fusion so you're not a star, that's a good start on what makes a planet. And most agree that size alone is not really good enough, because Mercury is smaller than Ganymede or Titan. And so the size and mass cutoffs you might use would essentially be arbitrary. Now, the shape of an object is a little bit fuzzy, because whether it's spherical depends upon its composition. If you are rock, you need a larger body in order to become spherical than if you are ice. And you could have a potato-shaped rock be more massive than a spherical snowball. And which do you call a planet? The more massive object, should that be the planet? Or the spherical one, should that be the planet? So shape isn't entirely clear whether it should be a major criteria. Now, when we consider orbit, there are some folks who question whether that's reasonable to consider, because the orbit of the object is not an intrinsic property of the body itself. It's just the dynamical property. And what orbit it's in is not really the object's fault. Could have been scattered out and moved around the solar system. So is it fair to call an object not a planet, or a planet based upon a property that isn't really intrinsic to the body? Now, I guess I would say that yes and no, that argument works, because orbit is part of a moon definition. Because Ganymede and Titan, as I said before, they're larger than Mercury, they would be called planets if they weren't orbiting Jupiter and Saturn respectively. Now, the one point of the definition that really gets the most discussion is the idea about dominating its orbit. And this is what you use to distinguish between whether it's a major planet or a minor planet. And I think, in my opinion, it's effectively the same criteria that we used for when we excluded the objects in the asteroid belt. So here is a plot that plots the object mass on the y-axis, and on the x-axis, it plots the amount of mass in the zone. Okay, so if you take an object's orbit, its perihelion to its aphelion, and you say how much mass is in that zone, that's what's plotted on the x-axis. And you can see for the 8 planets in the upper region of this plot versus the 2 asteroids and 2 Kuiper Belt objects in the lower part of this plot, there's a very clean separation. These diagonal lines represent constant ratios of mass of the object to mass in the zone. And you can see that Mars is the lowest of the planets. It's got a ratio of about 1,000, whereas Ceres is the largest of the small solar system bodies, and it's about value of 1. So this dashed line in the middle is the author's proposal for how you distinguish between a planet and a small solar system body, a minor planet, major versus minor. And he suggests that if the mass of the object is 100 times the mass in the zone, then you're a planet. Anything less, you're not a planet. That seems to work reasonably well. However, no matter what definition you come up with, there are a number of what-ifs to consider. Orbits can be unstable. So can an object change from being a planet to a non-planet if its orbit gets perturbed? If it gets sent into a different orbit, does it suddenly become not a planet? And what about a Mercury-sized object found in the Kuiper Belt or found out in the Oort cloud? Because Mercury wouldn't dominate the mass out in the Kuiper Belt, but we would consider it a planet interior when it's in the interior part of the solar system, and it's no longer a planet in the exterior part of the solar system. Does that make logical sense? And what about planets that are ejected? So Jupiter's mass has surely ejected a lot of comets. It may have ejected some planets from the solar system. These planets would then be traveling in interstellar space. They wouldn't be orbiting a star. So is actually orbiting a star a true requirement for a planet? And finally, what happens if other solar systems don't follow the rules that we create here for our solar system? Other proposals for definitions of the planet have been floated to try and address these ideas. And here's one that focuses on the formation of the object. It defines primary accreted objects as stars, brown dwarfs, and if you happen to form a planetary mass object as the central region of a collapsing disk, Then that would be like a substar. Then around that primary accreted object, you would form planets. And any ones that formed around those planets would be called moons. These would be your secondary accreted objects and your tertiary accreted objects. Everything else, the proposal calls them debris. Now, that's kind of a harsh term, and especially because Pluto would then go from being a planet to being debris. And wow, a lot of people would have problems with that. And furthermore, in this proposal, they say if it's not orbiting a star, you call it a rogue planet, a planet out in interstellar space. Some of these ideas are useful, some of these are not. The only thing we can really guarantee about the definition of planet is that it will be revisited as we discover more things. But in the end, I really have to question whether a definition is actually necessary. Two prominent Kuiper Belt experts have stated for the record they think no definition is needed. One of them points out this: there is no strict definition of what makes a continent on Earth. Is Australia a continent or is it an island? And if Australia is a continent, then how large an island qualifies? Does Greenland qualify as a continent or is it an island? What about Madagascar? And why is India a subcontinent? The point is not actually to figure out what a continent really is, but the idea that terms do not need to be strictly defined in order to be useful. For me, well, I fall back onto the families of the solar system. We know what the 4 rocky planets are. We know what the 4 giant planets are. We know about the families of asteroids and comets. And if you want to argue about this concept of planethood, it really just confuses the issue. Looking at the solar system in this way increases the understanding of the solar system and advances science. And ultimately, that's what we're trying to accomplish. In our next lecture, we're going to look at how this solar system organization came to be. What are the forces and processes that formed and shaped our solar system to make it look the way it is today? Until then, see ya.